All right, this video is going to be about energy, work, and power. You might find another set of videos on the website that has these topics broken up into work and power separately and energy and conservation of energy separately. Decided to pool these three together here at the end of the semester, so this is what you need to know for the set of notes that's called energy, work, and power. So to start off, we're going to talk about energy. Basically, there's two definitions that you need to know for energy. It's the ability to produce change in an environment, and these underlined lines are what goes in the notes. Change in an environment is more of a biological definition. If you think about any organism, it needs to have energy in order to order the environment that it lives in to increase the chances of its survival. And you can't do that unless you have energy. And second of all, for all organisms, the majority of that organism's lifetime is spent figuring out how to obtain and use energy efficiently. So energy is really important in biological systems, but obviously this isn't biology. A definition that fits really well with energy for physics is energy is the ability to do work. Now, if you think about the People Power Lab that you did in class, where you ran up the stairs and you walked up the stairs and you timed yourself for each one, you cannot do that work, climbing the stairs from the bottom to the top. You cannot do that work unless you have energy. The only way to do that work is to use your own energy that you have within your body. So energy is really, at the basic level, it's the ability to do work. We're going to define work here in a little bit. The common definition of work is not exactly the same as the physics definition for work. But you need to circle this part. You need to know that the unit for energy is joules, just like the unit for work. We're going to talk about that soon. But joules is a capital J because it's named after James Joule. So that's the unit for energy. So two definitions there for energy. There are a myriad of types of energy, many different types of energy, and we're going to talk about many of them in the upcoming semester. We're going to talk about heat energy, light energy, sound energy. But for right now, these two types are actually characterized as mechanical energy together. And mechanical energy is energy that is motion or energy that can produce motion. So the two types we want to talk about are kinetic energy and, specifically for us, gravitational potential energy. Now, potential energy in general, as this said, is just stored energy. Stored energy is energy that you're going to use later. You can store energy in the form of your lunch, that's chemical energy. You can store energy in a trampoline or a slingshot, that's spring potential energy, or a bowstring. But we're most concerned about the energy you're storing when you're climbing a cliff. That's gravitational potential energy, because you have the potential to fall. Your motion will be produced by the force of gravity. So this is gravitational potential energy that is stored. And then kinetic energy is the energy that you have when you're in motion. This prefix KIN means motion. It means to move. You're a kinesiology major in college. You're going to major in something to do with being involved in athletics, in which there's quite a bit of motion. So kinetic energy and potential energy, that's what they are. And then we're going to talk about the equations for each of them. We have an equation. I hit pause accidentally. Equation for each one. We're going to start off with kinetic energy. This equation is in the chart, but KE equals mv squared divided by 2, or sometimes known as 1/2 mv squared. KE stands for kinetic energy. So if you're given kinetic energy, it goes in right here. But we measure all forms of energy in joules, including kinetic energy. So all we're going to do for this equation is take the mass, which has to be in kilograms, multiply it by the square of the speed, and divide it by 2. Don't forget about PEMDAS. PEMDAS says that the first thing we have to do here is squaring the speed. We're going to do the exponent first. We're going to square that speed first, and then multiply by mass and divide by 2. We can actually do that in any order. It doesn't matter what order we do it in there. And then the other formula will be for gravitational potential energy. Don't forget that gravitational potential energy is when we're storing potential energy above some distance above the Earth's surface. And that formula is mgh. Potential energy is mgh. Once again, potential energy is measured in joules. If you're given potential energy, it goes in right here for PE, or you could be asked to solve for it. The way we solve for potential energy is m times g times h. M would be mass. G, really important that you know this. G we've used before, and it's the acceleration due to gravity. We've always used negative 9.8 because gravity always pulls us down, but it's so important to know that we're going to use a positive 9.8 for this, and I'll tell you why in just a moment. Actually, I'll tell you why right now. The reason is because energy is never negative. Let me go ahead and go to that slide and show you right here. Where is it? Where is it? I thought I could go to a certain slide. It doesn't do it for me. So I'm going to go ahead and go to this slide right here. It says that energy is not a vector, which means it cannot be negative. It doesn't have a direction. So we always want positive energy. We like people with positive energy. We like positive vibes. We don't like negative energy. So that's a good way to remember it. For that reason, we're always going to use positive 9.8 for gravity if we're dealing with energy, right? So to calculate potential energy, we're going to take the mass and multiply it by positive 9.8, and then we're going to multiply that by the height you are above the ground. Now, I want to take a minute real quick and help you understand something. So we just talked about the formula for potential energy is mgh. Oops, you can't see that. mgh. This mg, you might think, I've seen that before. Well, you've seen it here in this equation that we've used before. Fg, no, that's not it. Fg equals mg. Fg equals mg. Fg stands for the force of gravity, which is another term that we use for an object's weight. Y'all, it's hard to write and talk at the same time. You misspell things, you write things wrong. Fg is an object's weight. To get the weight, we took the object's mass and we multiplied it by, in this case, whenever we calculated weight, we used negative 9.8 because the weight always pulls down, okay? But for us here, we're actually just going to remove that negative because, remember, all energy has to be positive. That's what we just talked about. So the point is, mg is also what we see right here. In other words, all potential energy really is the magnitude of your weight, right? You're going to take your weight, because that's mg, and multiply it by however high you are above the Earth's surface. So potential energy is weight times height. So you might be given an equation or a problem that gives you mass, right? Mass is in kilograms, and you would do mass times 9.8 times height. Or you might be given a problem that gives you the weight of an object. Say the object has a weight of 100 newtons, right? And imagine that it is 10 meters above the Earth's surface. And the problem might say, how much potential energy does it have? Well, potential energy is just weight times height. So it would just be 100 newtons times the height of 10. 100 times 10 would be 1,000 joules of potential energy, weight times height. So if you look here in the notes, there are a few practice problems that we need to look at. These are so easy. These are super simple. We're going to go through these so fast. It says an 875 kilogram car is traveling at 44 meters per second while passing another car. How much kinetic energy does it have? This is the same stuff we've done all along. What are they giving you? What are they asking for? We're given the object's mass and its velocity, and they ask for kinetic energy. So the equation would be Ke equals mv squared over 2. Okay, so we write that formula down. We plug in the numbers. 875 is the mass, 44 is the speed, over 2. And then all we got to do is calculate that stuff. The way we do it is square the 44 first. So you would do 44 squared, multiply that by 875, and then divide what you get by 2. And the answer there is 847,000 joules. You see the other three worked out on the screen right now. I just want you to pause the video and in your own notes try to work those without looking at these, obviously, and then come back and I'll talk through them. All right, so this one we had a mass of a ball and give you the height, asks about gravitational potential energy, which is mgh, mass times 9.8, remember we use positive 9.8, times the height of 425. So we did 50 times 9.8 times 425, it gave us 208,250. The third one is a little bit different because instead of mass, they're giving us kinetic energy. That's our KE, and it goes in for KE. Running at a speed of 10, 10 goes in for our V, and we want to know mass in this one. We're trying to solve for the mass. So we plug the numbers in this way. 550 is the KE. Leave M there because we're trying to solve for the mass. 10 is V over 2. We're going to square the 10 first. You get 100. And then we do 100 divided by 2, which is 50. So we did 550 equals m times 50. And then we're going to divide by that 50 on both sides to get rid of it there. 550 divided by 50 is 11 kilograms. That's how we got that. And that's just an indication, that's just to let you know that you could be asked to solve for any of these variables either in this equation or in this one. It just takes a little bit of algebra.